In this presentation, I want to discuss one particular kind of system that sort of straddles the line between linear and nonlinear systems. To best understand this, let's consider an example. So our example is y of t is 3x of t plus 2. Is this system linear or nonlinear? Well, the gold standard for testing linearity or nonlinearity is to test whether superposition holds. So let's examine that first. Now, superposition is a combination of two properties, homogeneity and additivity. So let's first check homogeneity. We'll look at the response to two inputs. The first input is x1 of t equal to 1, and the second input is twice that, x2 of t equal to 2. Now, if homogeneity holds, if the input is twice as big, the output should be twice as big. But we find that the response to x1 of t is y1 of t equal to 5, and the response to x2 of t is y2 of t equal to 8. Now 8 is not twice 5, even though 2 is twice 1. So homogeneity does not hold. This means the system must be nonlinear. This system doesn't seem to have any of the bad properties that we expect of nonlinear systems. We're not seeing subharmonic behavior or the output going to infinity in finite time or anything like that. It's not chaotic. In fact, what this system does can be really easily understood, so it doesn't seem to be as bad as a nonlinear system. But technically, it is a nonlinear system. It does not have superposition. Now, this system would have homogeneity if the 2 was not present in the equation. In fact, the system would be linear if that 2 was not there. This 2 is called a bias. It's added to the 3x of t and kind of shifts it. Systems with a bias are called affine. Affine systems, while technically nonlinear, really aren't that bad at all. In fact, by doing a simple change in the output, we can actually make the affine system into a linear system. All we have to do is define a new output, y bar, which is the original output, y of t, with 2 subtracted from it. Once we do that, the relationship between the input x and y bar is y bar equals 3x of t. And of course, that's a linear system. So once we've redefined the system output, we're able to use all our linear analysis tools to examine this system. This is the reason why most practicing engineers would consider this system to be linear, because it's so easily transformed to a linear system. When we redefine the output in this way, all we're doing is reassigning where the origin of our coordinate system is, if our output is measuring, say, displacement. And of course, a fundamental property of a system, like linearity or nonlinearity, should not depend on something as simple as where we defined the 0 of our coordinate system. So even though affine systems are technically nonlinear, I want you to think of them as linear systems, because they're so easily converted to linear systems and so easily analyzed. And there's nothing at all to be worried about when dealing with a system that's affine. Now, if you're concerned about how to answer a question about an affine system on a test, don't worry about it. I won't give you any affine systems on any tests.